Good afternoon, everyone. Before we begin, if you can all please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, please feel free to introduce yourself, your name, your position, company, and which country you are based in. So it is great to see an international audience of people from all industries and backgrounds. Nice to see you all. Okay, great. Thanks for confirming. Thank you all for registering and taking time out on a Sunday to learn about implementation of active and passive fire protection systems, engineering and design. My name is Dania Basit, and I'll be your introductory speaker. It'll be our pleasure to host this webinar for you. This is our 67th webinar in a series of technical webinars we're conducting. As a practice, we're conducting one webinar every month. So please follow us on LinkedIn and make sure to check our website to stay tuned to the latest updates. Today, we have quite an experienced panel of speakers here for you today. I'm with my colleagues, Mr. Ijaz and Mr. Farasit, who are experts in this field, so you're all in good hands today. Moving forward, during this webinar, we encourage you all to keep asking questions to clear any doubts. We would like your engagement on this topic. This can not only help you, but also many others who can usually have the same doubts. You can type your queries in the Q&A window and you will either receive a reply in the window or we will answer it live. We'll try to answer as much questions as possible during this session. Furthermore, we have a detailed Q&A session after the completion of the topic. Please accept our apologies if your question is not addressed due to high volume of questions we usually receive. We must be selective. Moving forward, we will also be issuing participation certificates to all those who have attended at least 80% of the webinar and have participated in the discussions through Q&A sessions. Following our agenda, since this is quite a technical subject, and today we will be touching key theoretical and practical aspects of implementation of active and passive fire protection system engineering and design. In this limited time of 2 hours, we request you all to follow along with us, keep asking questions to help us in making this as engaging as possible. Please note that the client name and data have been redacted in this practical case study. We will be following a practical approach where we will walk you through the key steps through this case study. Before we begin, although most of us are in the comfort of our home, we should be aware of emergency exits. We should keep a safe distance and in general take care of ourselves and of those around us.
Thanks, Ms. Dania. So my name is Farasatullah Khan. Mr. Ijaz will join us shortly as well. So let us start our today's webinar, which is implementation of active and passive fire protection system, engineering and design. First of all, we will discuss the basics. For example, we will start by what is fire. Fire basically is a visible effect of the process of combustion. It is a very special type of a chemical reaction. It occurs between oxygen in the air and some sort of fuel. The fuel must be heated to its ignition temperature for a combustion to occur. The reaction will keep going as long as there is enough heat, fuel, and oxygen. And this is known as fire triangle. So understanding the 5 different classes of fire can help you determine the biggest fire risk at your facility. There are different type of, or we can say there are different classes of fire. Class A fires, also known as ordinary fires. These are most common of the 5 different classes of fires. They occur when common combustible materials like wood, paper, fabric, trash, and light plastic catches fire. These accidental fires are ubiquitous across a variety of industries. So it is recommended to have adequate protection against ordinary fires in addition to the condition-specific fires. And yes, despite being ordinary, we should not rule out this class of fire as low risk. Second class of fire is class B fires, which are also known as liquid or gaseous fire. Class B fires involves flammable liquids and gases, especially fuels like petroleum or petroleum-based products such as gasoline, paints, and kerosene. The next type of fire is Class C fires. And before going to Class C fires, in Class B, other gases are also highly flammable, like propane and butane, which are common cause of Class B fires as well. The best way to deal with these type of fire is by smoothing them or removing oxygen using foam or CO2 fire suppression equipment. Now, class C fire, which is also known as electrical fire. Electrical fire falls under class C and are common in facilities that make heavy use of electrical equipment, but they cannot occur in a wide range of industries. For example, data centers. Data centers might be an obvious risk area of class C fires. They must have safeguards in place to deal with electrical fires. Another example is also construction sites for this class C fires as well. So basically, these electrical fires require non-conductive material to extinguish a flame, so that this water alone is not a good solution for these electrical type of fire. Facilities with sensitive equipment may prefer clean agent suppression because it won't leave residue or damage electrical equipment. The next type of fire is class D fires, which are also known as the metallic fires. So these class D fires are not common as the other classes like A, B, and C, but they do require special attention because they can be especially difficult to extinguish. Metallic fires involves flammable materials like titanium, aluminum, magnesium, and potassium. All these are commonly available in laboratories. Class D fires cannot be addressed with water, as this can be exacerbate the fire and be potentially dangerous. For this class of fires, class D fires, dry powder agents are the best solution for smoothing the flames and limiting the damage to property or people. The next class of fire is class K. It involves flammable liquids similar to class B, but are specifically related to the food services and restaurant industry. Also, this is also known as kitchen fire as well. These common fires start from combustion of liquid cooking materials, including grease, oils, and vegetable and animal fats, because they can spread quickly and be difficult to manage as well. These class K fires are some of the most dangerous, and water can make the situation even more worse. But smoothing the flames or using a wet agent fire extinguisher is effective for this type of fires. These are the different type of fires, I should say hydrocarbon fires. Hydrocarbon fires are principal concern in many processing facilities. There are many different type of hydrocarbon fires like jet fires, unconfined vapor cloud fires or flash fires, pool fires, which is two-dimensional fires as well. Then running liquid fires, which is also known as three-dimensional fires, and then boiling liquid expanding vapor explosions or fireballs. Now that we understand how each fire starts, we can prepare for how to fight them, or better yet, prevent them from happening in the first place. So these are different type of agents and different type of extinguishments are written in this table, advantages and limitations as well. Different type of fire extinguishers exists in order to address the 5 different classes of fires. Each fire class describes the fuel or material a fire is burning or what causes to start. Therefore, using the right extinguisher is essential to put out the fire safely. This is a quick chart to help you identify the right fire extinguisher for each class of fire. For example, class A fires, which are the ordinary and combustible materials, we can use water-based fire extinguisher, foam, dry chemical, wet chemical, and clean agents, but we cannot use dry powder and carbon dioxide. For class B fires, which are these are the flammable liquid and gases, we cannot use water and wet chemicals and dry powders. We can only use clean agents, carbon dioxide, dry chemicals, and foam. Similarly, for electrical type of fires or class C fires, we cannot use water type fire extinguishers or foam or wet chemicals or dry powders. We can only use clean agents, carbon dioxide, dry chemicals. Then for class D fires, we can only use dry powders, which are for the flammable metals like magnesium, titanium, aluminum. And then for kitchen fires or cooking oil or grease, class K fires, we can only use wet chemicals. Now let us discuss the fundamentals of fire protection by discussing the importance of fire protection. This is the incident occurred in 1984. It was the major fire and a series of catastrophic explosions occurred at the government-owned and operated Pemex LPG terminal in Mexico City. This incident resulted in 650 fatalities and more than 6,400 injuries. What were the lessons learned from this incident? the lesson learned was that emergency isolation was not provided. Fire protection system or fire protection was minimal. The layout and spacing allowing the escalation of the fire and understanding of the potential fire risks were lacking in the industry. These are the applicable standards and codes. These are for the NFPA. It is a wide range of, it provides wide range of standards from NFPA 10 to NFPA 2001. NFPA 10 is a standard for portable fire extinguishers. Then NFPA 11, it is a standard for low, medium, and high expansion foam. Similarly, NFPA 2001, which is a standard on clean agent fire extinguishing systems. So we have other type of standards as well, like American Petroleum Institute standards, and then IP standards as well. Now, let us discuss what is fire protection and what is fire prevention, how we define fire protection and how we define fire prevention. For fire protection, we can say that the science of reducing loss of life and property from fire by controlling and extinguishing. Fire protection includes fire prevention, detection of a fire, providing systems to control or mitigate the fire, and providing manual firefighting capabilities. Then what is fire prevention? Activities whose purpose is to prevent the fires from starting. Fire protection and fire prevention go hand in hand. All fire protection programs include a fire prevention program as well. For example, control of ignition sources is very important in minimizing the risk of fire, but does not meet the definition of fire protection in this guideline. We will discuss the fire protection strategy as well. For the fire protection pyramid as well. So the fire protection strategy is a systematic approach to identifying, reducing, and managing fire hazards. Then these are the objectives of fire protection strategy. It starts by the protection of personnel is considered in design of fire protection systems. Whether the credible hazards have been identified, credible hazards have been assessed, understood, and documented. Every opportunity to minimize the hazards has been identified, considered, and where practical, implemented or no. Then the capital investment and estimated operating expense is optimized with a view to minimizing the hazards. Then corporate goals can be met for the facility's lifetime. Potential adverse effects on neighbors, community, and the environment are controlled. So these are the objectives of the fire protection strategy. This is the risk management system. It involves risk management system philosophy. For example, what a company believes, what are their approach to hazard management, and what are the risks they are willing to accept. It also involves strategies that how and when a company plans to execute their philosophies, like inherently safe design, risk assessment, emergency response, fire protection, project design reviews, safety management systems, and also it involves procedures as well. So fire protection procedures describes how to implement the fire protection strategy. So this is about the installed systems versus the emergency response. There are 5 main strategies in providing adequate fire protection of a facility. It involves installation of active fire protection and installation of passive fire protection. We will discuss this active fire protection and passive fire protection in details in the upcoming slides. And the third one is install the isolation systems to minimize the fuel. Emergency response by organized firefighting teams composed of both on-site and off-site fire brigades using mobile units to extinguish the fires at the facility. Incipient firefighting, and if the fire becomes too large, protect the exposures and walk away. So active versus passive fire protection. What is active fire protection system? Active fire protection system requires some action to occur before it functions per its design intent. This action may be taken by either a person or control system. Examples of active fire protection systems are fire water pumps, detection and alarm, gas sensing detectors, sprinklers, water spray systems, water mist systems, foam systems, foam water deluge, water suppress systems, clean agents, carbon dioxide systems, dry chemicals, steam snuffing, portable fire suppression systems, hydrants and monitors, emergency isolation valves, and ESG system. So we will discuss these examples of active fire protection in details in the upcoming slides as well. Then the passive fire protection system. This passive fire protection system requires no action to occur for it to function per its design intent. Examples of fire protection methods are fireproofing, spill containment and drainage, diking, firewalls, electrical area classification, static electricity lightning and stray current protection, and passive fire protection also involves physical separation of units and buildings. So this is a detail of active fire protection, that active fire protection system can be installed to provide the desired mitigation by either automatic or manual activation. How we can mitigate by providing the automatic activation, and what is the automatic activation? The answer is the automatic activation is a system where fire protection devices are integrated with a detection system designed to automatically activate upon sensing the fire. Increased cost of initial installation due to inclusion of the activation system, additional maintenance is required, damage that could occur due to automatic activation. Then what is manual activation? And for automatic activation, there is a chance of spurious activation as well. So it can cause damage as well. Now, the manual activation requires a person to activate the system by pushing a push button or opening a valve in response to either an observation of a fire or a signal from detection system. Additional emergency response capability may be required because the fire may be larger and escalation is more likely for the manual activation. Surveillance capability, availability of a personnel. So if the person is not available, then he cannot activate manually. This is a drawback. And then if a delay in activation occurs, the fire may be larger and longer, resulting in more property damage in terms of cost. So how we can minimize or mitigate by providing the isolation? Process fires will continue and may escalate until the flow of fuel is stopped. So for the fire triangle, three things are necessary: fuel, oxygen, and heat. So the process fires will continue and may escalate until the flow of fuel is stopped, the fuel is fully consumed, or the fire is extinguished. Isolation valves are used to reduce or isolate the inventories of flammable gases or liquids. Isolation valves may be located near the property line, the edge of the process unit, or the liquid outlet of the vessel. Valves should be installed on all the hazardous material lines entering or leaving the facility to ensure the facility can be isolated in event of a spill or fire. Similarly, valves should be located at or near the battery limit of each unit or outside dike walls for the same reasons and for the safety and ease of the access. Equipments such as pumps, compressors, tanks, and vessels associated with the large inventories of the flammable gas or liquids should be provided with equipment emergency isolation valves to stop the flow of material if a leak occurs. Then what is depressurization and how we can mitigate with the help of the depressurization? When the shell of a vessel is exposed to the extreme heat on the outside and inside is in contact with vapor, metal temperatures may reach levels where tensile strength will be reduced such that rupture may occur, even though the pressure does not exceeds the set point of the pressure relief valve. Vapor depressuring provides fire protection of process units by reducing the contained pressure at such a rate that there is a significant reduction in the chance of rupture of any steel pressure vessel exposed to fire. The driving force behind pressure jet flames is rapidly decreased. The leakage rate of liquid spills decreases, allowing containment of pool fires. There are several advantages of vapor repressuring, including the following. An auto refrigeration effect may be produced in a pressure vessel, which provides cooling of a liquid contained in the vessel. The need for a liquid flow down system is eliminated by retaining liquid in the vessel as a heat sink. Any increase in temperature of the wetted shell is minimized. Then, how we can mitigate the escalation of fire with the help of emergency response? Emergency response has a significant influence on the company's fire protection strategy. The question arises that to fight or not to fight fires at the facility. Emergency response is one of the last layers of protection available to the facility. No matter how a company may provide emergency response, they must comply with federal, state, and local regulations. Emergency response can be internal resources, external resources, or a combination of both, internal and external. The degree of internal response can vary from basic ability to properly respond with fire extinguishers and sound the alarm to a fully fledged industrial fire brigade with internal structure firefighting capability. External response may include local fire departments and mutual aid organizations outside the facility. Now, we will discuss the active fire protection system in detail. Fire water demand, how we can calculate what is the demand of fire water. So fire water demand is a maximum rate of water that will be needed at any one time and applicable to a single fire. Thus, the requirements of the largest single fire contingency will determine the capacity and design of the fire water system. The fire hazard analysis should serve as a basis for determining fire water demand. Normally, this design will be based on the assumption that there will be a single unit involved in the fire, where separation of units or hazardous equipment is less than 15 meters. The combined area should be considered as a single fire area. Water demands for other areas within the plant may include, for the utility plants, 1500 gallons per minute, loading racks, same, office building, workshops, storehouses, 1000 GPM, plus sprinkler requirements if specified, then cooling tower, 2500 GPM. Normally, fire water demands range between 2000 to 10,000 gallons per minute. So if the design water flow rate for the process unit requiring the largest flow is less than the requirement for the largest tank or a group of the tanks, the tank protection demand should become the design basis. The design capacity of the fire water system should be a minimum 4 hours of continuous operation of the largest fire water demand. The capacity is based on the number of factors, which includes isolation philosophy and the ability to depressurize the high pressure units, sources of water available, potential for escalation to other areas of the facilities, as well as the reliability of makeup water supply as well. The reliability of the fire water supply should be such that the loss of any one source does not result in a loss of more than 50% of the flow requirements of the system. So the design capacity of fire water system should be minimum 4 hours of continuous operation of the largest fire water demand. How we can distribute the water? So water distribution within a facility involves fire mains, valves and fittings, and fire hydrants and monitors. What are the fire mains? Fire water mains should be designed to handle the maximum pressure developed by fire water pumps. Valves in a fire water system should be a type such that their position, open or closed, can be readily determined. For example, rising stem, post indicator. And hydrants and monitors should be placed so that they can be safely utilized during a fire, such that the total firefighting and equipment cooling water requirements for each fire area can be delivered. So what should be the fire water pumping capacity? What should be the flow rate? So the fire water pumping capacity should be sufficient to provide the required amount of water at required pressure to the fire areas having the greatest demand. At least 50% of the pumping capacity should be from diesel-driven pumps. fire water pumps should have a minimum capacity of 1500 gallons per minute and can range up to 5000 gallons per minute. It is common practice to provide pumping capacity so that when the largest fire water pump is out of service, the total fire water demand can be met. Each pump should be subjected to full acceptance test, FAT, upon installation as specified in NFPA 20. Now we will discuss detection and alarm system. So basically this detection and alarm system is for reporting the fires and alerting the plant fire brigade, and multiple fire departments should be provided. This system should be as simple as possible to minimize the potential for confusion in emergencies. Number of factors must be considered in design of the reliable fire detection and alarm system, which includes data on the nature and arrangement of power sources, coverage provided by the system, alarm function on loss of system operability, suitability of detection devices for risk involved, testing and maintenance procedures to ensure a reliable system, and then consequences associated with false alarms. Then it comes the sprinkler system. These are the common fire protection system used today. In offices, buildings, you must see this type of system. The success of fixed water suppression system depends on the following. It needs adequate and reliable water supply. This sprinkler system needs adequate water density, automatic actuation of the system, effective water spray patterns, alarm that indicate the operation or malfunction of the system, and effective maintenance and testing is required for the sprinkler system. So there are 4 basic types of sprinkler systems. It involves wet pipe, dry pipe, pre-action, and deluge as well. So wet pipes are the most common and least complicated of all sprinkler systems, where all the pipes are normally full of water. That's why it is known as wet pipe. Dry pipe is a sprinkler system which is developed to provide sprinkler protection for unheated buildings in cold climates. Also, a dry pipe sprinkler system can be used to minimize the corrosion as well, with respect to wet pipes, in comparison to wet pipes. Then pre-action. The principal difference between a pre-action system and a standard dry pipe system is that in the pre-action system, the water supply valve is actuated independently of the opening of the sprinklers. Then it comes deluge, which is also a type of a sprinkler system. Deluge protection can be applied over the entire hazard area with open sprinkler heads located at various floor levels, or fixed water spray systems can be applied, especially on the equipment to be protected. So the design of a fire, this sprinkler system should be in accordance with NFPA 13. Then water spray system. So basically this water spray system is hydraulically designed with open spray heads to protect a specific hazard. This term water spray basically refers to the use of water discharged from nozzles having a predetermined pattern, droplet size, velocity, and density. While deluge systems are for the overall protection of the given area, water spray system can be installed for the protection of a given area for specific equipment or hazards. This water spray system should be designed in accordance with NFPA 15. These water spray systems are used for protection against hazards involving gaseous and liquid flammable materials and combustible solid materials. Then what is this water mist system and how it is different from water spray system? Water mist system is also a fire protection system using very fine water sprays. The very small water droplets allows the water mist to control or extinguish the fires by cooling of the flame and the fire plum. oxygen displacement by water vapor, and radiant heat attenuation. Water mist systems are intended for rapid suppression of fires using water discharged into completely enclosed limited volume spaces. Water mist systems are desirable for spaces where the amount of water can be stored or that can be discharged is limited. So the potential applications of water mist systems are flammable and combustible liquids, electrical hazards such as transformers, switches, circuit breakers and rotating equipment, and electronic equipment as well. Then foam system. Foam system or foam is primarily used for extinguishment of two-dimensional surface fires involving liquids that are lighter than water. Foams may be used to insulate and protect against exposure to radiant heat. Because of water content, foams may be used to extinguish surface fires in ordinary combustible materials such as wood, paper, rags, etc. Foams are arbitrarily subdivided into three ranges of expansion, roughly corresponding to certain type of usage. It involves low expansion foam, medium and high expansion foams. So what is the volume of low expansion foam? Expansion up to 20 times to the foam to solution volume. Medium expansion foams are the expansion from 20 to 200 times foam to solution volume. And high expansion foams are the expansion to from 200 to 1000 times foam to solution volume. Foam systems have more components requiring higher maintenance and have somewhat lower reliability than water-only systems. Foam systems are designed in accordance with NFPA 11. There are different methods of application of this foam system. It involves fixed systems, fixed, semi-fixed systems, and portable systems. Fixed systems are complete installations piped from a central foam station to tanks or equipment, discharging through fixed delivery outlets. And then semi-fixed systems employ fixed discharge outlets connected to permanent piping that terminates at the safe distance from the tanks or equipment to be protected. Then portable systems contains no fixed foam piping. Foam is delivered to the spill or burning surface by hose streams or portable monitors. So how we can proportionate the foam? And for example, we required a low expansion foam, medium expansion foam, or high expansion foam. So in order that a predetermined volume of a liquid foam concentration may be taken from its source and placed into a water stream to form a foam solution of fixed concentration, the following two general method classifications are made. First is methods that utilize external pumps or pressure to inject concentrate into a water stream at a fixed ratio. And then the methods that utilizes the energy of the water stream by venturi action and orifice to induce concentrate. Typically such devices impose a 35% pressure drop on the water stream. So application of foam for suppression of tank fires. This number of foam discharge outlets, for example, the tank diameter is up to 80 feet or 24 meters, then how many number of foam chambers are required? And what will be the subsurface classes of liquids are required and class 3 liquids are required. So properly applied firefighting foam can be an effective fire suppressant for most flammable or combustible liquids stored in vertical cylindrical tanks. Then foam water deluge system. The foam water sprinkler system is basically the same as sprinkler system, except foam concentrate is proportionate into the water, causing foam to be discharged. These systems can flow either water or foam effectively. The foam system should be designed in accordance with NFPA 16. The foam discharge rate for the foam sprinkler system should be at least 0.16 gallon per minute per foot square. The foam discharge should be continuous for a minimum of 10 minutes. With the exception of high expansion foams, all other foams can be used in foam water sprinkler system. However, AFFF is the most versatile agent because of its spreading capability, and it can be applied through ordinary sprinkler heads. Then clean agent system. These clean agents are electrically non-conductive, volatile, or gaseous fire extinguishing agents that do not leave a residue. Clean agents fall within two categories. First is hydrocarbons and inert gases. Typical hydrocarbon includes hydrofluorocarbons, HFCs, hydrochlorofluorocarbons, HCFCs, perfluorocarbons, and fluorohydrocarbons as well, FICs. Typical inert gases includes argon, nitrogen, carbon dioxide, or combinations of these agents. These can be used in the substations, which contains electrical and electronic equipment, subfloors and other concealed spaces, flammable and combustible liquids, telecommunication equipment. So the designing of this clean agent system is, we have to follow NFPA 2001. Now, the carbon dioxide system. This carbon dioxide system should be designed and installed and tested in accordance with NFPA 12. Fixed CO2 system may be total flooding or total application systems. Now, what is total flooding system? This type of system may be used where there is a permanent enclosure around the area or equipment to be protected that is adequate to enable the required concentration to be built up and to be maintained for the required period of time to ensure complete and permanent fire extinguishment. And then it comes local application system. This type of system may be used for extinguishment of fire surfaces, fires and flammable liquids, gases, and solids, where the hazard is not enclosed. Examples of hazards they may be successfully protected by local application system includes dip tanks, quench tanks, and spray booths. Now, what is dry chemical system? Dry chemicals are recognized for their unusual efficiency in extinguishing two-dimensional fires involving flammable liquids. Fast extinguishing action is achieved providing the agent engulfs the fire without interruption of the application. These agents are effective on small spill fires. If there is a risk of reignition from embers or hot surfaces, these ignition sources should be quenched or cooled with water and secured with foam, or the source of fuel should be shut off before attempting extinguishment. Dry chemicals agents are non-toxic and are suitable for extinguishing clothing fires on individuals as well. Now, what is portable fire suppression equipment? Based on the physical layout of the site, the hazards of the process and the fixed fire protection systems, additional fire suppression equipment may be required to effectively manage the fire emergency. Portable fire suppression equipment assist in providing fire protection for the equipment involved in an emergency situation. Examples of these portable equipment includes fire extinguishers, fire water monitors, foam tanks, foam eductors, water tanks, special high flow nozzles, trailer mounted fire water pumps, water foam pumper, aerial and ladder fire trucks as well. The use of this portable equipment provides the protection where the cost of fixed system may not be acceptable or the fire water supply may be limited. Now we will discuss the case study. basic engineering study for the fire risk assessment implementation phase 1. We will discuss the objective of this case study and what was the scope of this case study. This is the project background. The HSE gap assessment audit was conducted for all the upstream facilities of the client, and various recommendations were made to improve the following systems: fire and gas detection system, active firefighting system, passive firefighting system, HSEMS, and associated control procedures as well. We have to carry out front-end engineering design and development of HSEMS related documentation in accordance with the requirements identified during the gap assessment studies. So what was the objective? The project objective was field engineering for fire and gas detection system, designing of active and fire protection systems, development of HSEMS related documentations in accordance with the requirements identified during the gap assessment studies. There were different facilities, and scope of each facility was different to the other. For the facility A, the scope was we have to calculate the fire water demand. Then we have to design the automatic gaseous flooding system for control room and electrical room. Then we have to design the automatic sprinkler system for the living quarters. Then fire water curtain system at escape routes. Then we have to perform the study by removing the existing detectors and to install the new toxic gas detectors and flammable gas detectors. New instrumented automatic fire detection for process equipment for all the production platforms. So this was the scope for facility A. For facility B, the scope of this case study was to remove the existing detectors and installation of a new toxic gas detectors and flammable detectors as well. Removing existing detection and design and install the new fire detection system for building and process equipment with centralized control system. It was a part of a scope. Then for facility C, the scope was we have to replace the bladder tank foam system. We have to basically install the bladder tank foam system in place of PPT system with 100% connected reserve. Number of foam chambers to be designed as per NFPA 11 standard. Then we have to design the automatic gaseous flooding system for MCR, sprinkler system for dining hall at camp A, C, and lab. So then we have to perform a study by removing the existing detectors and to install a new toxic gas detectors and flammable gas detectors. And then removing the existing detection and design and installation of a new fire detection system for building and process equipment and tank farm with centralized control system. Similarly, for the facility D, the scope was additional requirements for FM200 system at SCR, station control room, removing of the existing detectors and installation of a new toxic gas detectors and flammable gas detectors, and then removing of the existing detection and design and installation of a new fire detection system for building and process equipment with centralized control system. This was our methodology which we followed. First of all, the project was started with the kickoff meeting, and then we have collected the data. Then it involves the site visits, surveys, and collection of the required information. And then updating of design basis memorandum followed with the FNG mapping study and checking of the existing fire water system adequacy and integrity as per scope. And then we prepared the basic engineering deliverables. The list of deliverables will be coming in the upcoming slides. Then internal QA/QC, and then cost estimation, purchase requisition of long lead items, and EPC tender package as well. So this is the flow chart of the methodology. So what standards and codes were referred? It involves the national or local standards, then the client standards, which we have performed this field study, and then NFPA standards, HSE UK Executive API, IP standards, ASME standards, and then Shell best engineering practices. These were the list of major deliverables what we have prepared as a part of a scope. We prepared the far water demand calculation report, design basis memorandum, basic engineering design data, project coordination procedure, document numbering procedure, document control register, site survey and document retrieval reports, project basic design dossier, EPC scope of work, cost estimates, EPC tender package. And then we delivered project execution schedules, bill of materials quantities, project HSE plans, long lead items list, long lead item RFQs, specification of material procurement, specification of test and commissioning, QA/QC procedures, site test specification, transportation vessel requirements as well. So these were our deliverables for this case study. Now, how we designed the sprinkler system for the client. So basically, the sprinkler system design at facility living quarters, there were RFA report and gaps and recommendations were provided in that report. These were at living quarters without sprinkler system, personal life is at risk as chance of escape will be less, especially in offshore platforms, and potential loss of life will be high. The people life is at high risk as living quarters fall within the radius of 12.5 radiation contour from production spectator at CPF platform. So these were the basically recommendations and gaps. Living quarters at CPF are to be protected with automatic sprinkler system. The automatic sprinkler system is to be designed as per NFPA 13. So for the implementation of this recommendation, there are below listed 3 levels of living quarters at CPF, where we have to provide the automatic sprinkler system. 3 levels. First level was main deck, then level 1 and level 2. This is offshore. This was the offshore plant. So what was the design criteria? NFPA 13 edition 2013, which is a NFPA 13 is a standard for installation of sprinkler system, is mainly referred for carry out the design of sprinkler system for living quarter at this client facility. Living quarters are considered ordinary hazard occupancies, group 2. Then we considered wet pipe sprinkler system for the living quarters. Frangible glass pulp type sprinkler nozzles having temperature rating range 57 to 77 degrees C is selected on the basis of maximum sealing temperature, which was 38 degrees C as per NFPA 13, table 6.2.5.1. The maximum allowable protection area for coverage for a sprinkler is taken 130 foot square as per NFPA 13, table 8.6.2.2.1b. The maximum spacing between sprinklers is taken as 15 feet, which is equivalent to 4.6 meters as per NFPA 13, same table. And then the spacing between these sprinkler branch lines is taken 12 feet on the basis of maximum coverage area per sprinkler nozzles. The dimensions: length width and height of each room at all three levels of living quarters, which involves main deck, level 1 and level 2, are measured during the site survey and marked on CPF layout, living quarter plans, living quarter side elevations. Then the layout drawings are developed as per the dimensions measured during the site survey. The elevation of the ceiling for all the rooms at the living quarters is 2.27 meters. As pendant types of sprinklers are considered, so these would be installed at ceiling level. The elevation of the main deck from Trident 7 level is taken as 3 feet. The design density for sprinkler system for main deck level, level 1 and level 2 living quarters is taken on the basis of calculated area as per NFPA 13 figure 11.2.3.1.1. Then 10% additional water demand is considered in calculation for hydraulic imbalance as per standard engineering practice. Then fire hydrants are already available at these living quarters. So no whole stream is considered for sprinkler system and living quarters. It is to be checked and verified. We checked and verified this during the APC stage. Hydraulic calculations are performed by using pipelet software. We used version 1.5. Hydraulic calculations are carried out on the basis of Hazen-Williams equation as per NFPA 13, section 23.4.2.1.1. C factor used in Hazen-Williams equation is taken as 120 as per NFPA 13 table 23.4.4.7.1. Water viscosity and density are taken as 2.42 pounds per hour and 62.32 respectively at 68°F for hydraulic calculations. Nominal K factors for pendant type nozzle is taken as 5.6 and half-inch NPT is considered as per NFPA 13 table 8.6.2.3.1 for fire water sprinkler nozzle. Then equivalent length of the fire water pipe is considered as 1.5 times of pipe's straight length since piping isometrics are not available at that time. Minimum operating pressure at remote sprinkler nozzle is considered as 0.4 A2 bar as per NFPA 13. The minimum required pressure at all the three sprinkler systems inlet tie-in points is hydraulically calculated on the basis of minimum required pressure at remote nozzles. Normal allowable velocity limit for fire water sprinkler system is considered as 6 meters per second as per NFPA 20. And the maximum friction loss value is considered as 1.5 bar. For the central processing facility living quarters area, the existing fire water piping layout and PNID is not available. So the fire water tie-in points for sprinkler water is not identified. However, the tie-in in connections for sprinkler system can be taken from the discharge headers of the fire water pumps installed at living quarters or Trident 3 and where discharge pressure is 8.13 bar as per FRA report. Fresh water is considered for fire water sprinkler system as fire water at CPF Trident 3 area is fresh water referred from FRA report. So this is the calculation of the fire water sprinkler system, that how many sprinklers are required at each room, at each level of the CPF living quarters. The main deck level living quarters consist of men's rooms, warehouse, sick bay, laundry, and corridors where automatic sprinkler system is to be provided. So this is the individual rooms calculation. For example, it was 2 men's room. Length of this 2-man, 4-man room was 15.28 feet. Width was 7.09. So area, length into width, we got the area in feet square. So as per NFPA 13, the coverage area per sprinkler is 130 feet square. So dividing this by total area of a room, we will end up with the number of sprinklers required for each room. So total number of 2 men's room were 10. Total number of 4 men's room were 2. So total number of sprinklers required for all rooms were 12. 10 plus 2, because for each room, 1 sprinkler was required. Similarly, calculation for the warehouse, length was 15.28 feet, width of warehouse was this, area width, length into width, we will got 108.34 feet square. As per NFPA 13, the coverage area is 130. So area divided by coverage area, we will got the number of sprinklers 1. Similarly, same calculation for sick bay and laundry as well. Length into width, we will get the area, and as per NFPA 13, the coverage area divided by the coverage area, we will get how many number of sprinklers is required. So for laundry, number of sprinklers required were 2. Similarly, for the main corridor, same calculations. So these were the overall main deck calculations. So total number of sprinklers required were 23. Total area was this much. And as per the design density, as per NFPA 13, figure 11.2.3.1.1 is 0.19 gallon per minute per foot square. So what will be the fire water demand? Fire water demand is total area multiplied by design density. We will get 396.24 gallons per minute. So 10% additional hydraulic balance was required as per the scope of work. So fire water demand with additional 10% will be fire water demand into additional 10%. The answer is 435.86 gallon per minute. So in this way, the sprinkler system was designed at the main deck levels. So the hydraulic calculations for the main deck level living quarters are performed using the PipeNet software. We used version 1.5. Sprinkler system analysis is performed for the following. For sizing the sprinkler system network at main deck level living quarters, line sizing is performed by verifying maximum allowable velocity is not exceeded at any point in the network system. For finding out the required pressure at each sprinkler nozzle and at the inlet of sprinkler system so that each sprinkler nozzle pressure is maintained at the minimum of 0.48 bar gauge or 7 psig pressure. So these were the input data required for the hydraulic calculations of the main deck level sprinkler. Input nodes, output nodes, then diameter in inches, then length, elevation, C factor, which was used as 120. So this is basically the hydraulic analysis for the main deck levels for the fire sprinkler system. So as I told you earlier that we used the PipeNet software. So these were the results. Refer below for the piping network results for hydraulic calculations of main deck level sprinkler system. So input pressure required was this much for each label, output pressure, then friction loss, velocity, flow rate. For the other labels, so sprinkler nozzle results, refer below for sprinkler nozzle results for hydraulic calculations of main deck level sprinkler system. So available pressure at main deck sprinkler nozzles for each nozzle are this much, and the required pressure at main deck sprinkler system time points is calculated as 24.68 psig. So similarly for the other nozzles. So this is the conclusion of the sprinkler system design. For the installation of fire water sprinkler system at CPF living quarters, refer below for hydraulic calculations, fire water demand and time point pressure for all the 3 levels of living quarters. So fire water flow rate required for the main deck was 495 gallons per minute and time point pressure was 25.8. Similarly, for level 1 and level 2, we have calculated the fire water flow rate requirement and time point pressures. So calculation for level 1 and level 2 sprinkler system was done in a similar manner. Before going to the gaseous flooding system, we will take some questions. So, Mr. Kill.
Okay, here are some questions. What is the difference between dry chemical and dry powder?
Both are the same. Both are the same. No issue.
Okay, next question. Belvi or Fireball was mentioned in one of your slides. Can you implement AFP or PFP for BLEV? What is the code and standard describing the requirement?
See, for PFP, there is a API 2018, and PFP is an NFPA. So these are two standards which define the applicable fireproofing and active firefighting system criteria.
Okay, next question. Is it advisable to use foam to extinguish fire caused by class 3 products, such as heavy fuel oil or gas oil?
See, all the tanks which are storing these products, the primary firefighting tool is foam, and secondary is the cooling by water. There is a normal standard firefighting system for the oil storage tanks.
Next question. How is the protection of personnel considered in design? Fire protection usually is not provided to protect people.
See, when protection of the people means like people can act themselves. If there's a fire, they have to escape, right? The escape studies are like escape path and routes are provided, right? Then assembly points are defined where the people would be gathering. But firefighting system is for the fires, like where potential fire can take place, and people are the secondary or the affected area. For example, if there's a fire, asset can be damaged or destroyed. Secondly, people can be killed. So for active and passive fire protection systems are installed to take care of both aspects.
Next question. What is your feedback on providing PFP on isolation valves? Isolation valves are usually fail-safe and fire-safe, and during design, there is also a debate that isolation valves need to be fireproofed, considering they are fire-safe and fail-safe. Is there any international standard or code clearly specifying this requirement?
See, these are like, first of all, isolation valves, as it goes to the manual isolation valves or even control valves, they are not considered as a subject for passive fire protection, right, or fireproofing point of view. However, ESD valve and blow down valves, there is expectation that these valves would be able to act during emergency. For example, ESD valves are supposed to close at the ESD button pressed, and blow down valves are supposed to open. So there's a practice where actuators of these two type of valve, ESD valve and blow down valves, sometime fireproofed, sometime not fireproofed. However, for normal isolation valve, there's no requirement of fireproofing. The example is that these all valves are installed on the piping systems. And piping cannot be fireproof, otherwise there would be inspection constraints and there would be corrosion issues which you cannot manage. So someone can say that if walls are not fireproofed or not protected, what is the purpose of fireproofing the door, which is the valve? So it's a debate in the industry, but in normal practice point of view, as I said earlier, for isolation valves, manual isolation valves or control valves, there is no requirement of fireproofing. But for ESD valve and blowdown valves, there are contradictory practices. Somewhere fireproofing is done for the actuator, somewhere it is not done. So it is up to company to follow the practice.
Okay. Next question, sir. Usually it is electrical and diesel as standby combination. Can we implement diesel FW pumps 2 by 100% only?
See, diesel is a more preferable because diesel you can always control, whereas electricity is like if dependent on the power supply from some source. So if two diesels are preferably more good as compared to one diesel and one motor.
Next question. Difference between the sprinklers and water sprays.
See, it is only type of the like sprinkler nozzles or spray nozzles, right? And the purpose is as per the subject where you want to apply it.
Next question. During a drilling of oil and gas well, there are many chances of fire. How can we minimize it in the platform where there are too many chances?
No, see, when we say during drilling, see, drilling is a process when operation is not taking place there, and normally wells are more than 3,000 meters, 3,000 feet to 5,000, 8,000 feet. So the normal blow down or BOPs are blowout, basically, protections are provided during drilling. And if you see that the safety level in the drilling side is quite good. Yes, sometimes blowout can take place, and there are examples like a Mexican disaster for BP. Otherwise, there are secondary and tertiary protections are in place while doing the drilling operations, and active firefighting system by manual extinguishers and so on is in place.
Okay, next question. Please specify what is the contingency in case if fire sprinklers, any of the series, does not work in a particular area.
See, then there's a manual intervention. You can send the fire tenders, they can take care, but there's no other option other than the installed system.
Are combustible liquid or flammable liquid hazardous to human health?
Generally, like normal petroleum products are not hazardous for human health, but if fire is there, then yes, burning would be there, and it's very, very dangerous. And if they contain toxic elements, that's also a secondary area of health issue.
Okay, next question. High expansion foam is required or applicable to which facility?
See, those are the standard type of the foam substrate which are available and applicable. And these are as per NFPA, I think 11, when we define the applicable substrate material for the foam.
In data centers, which type of FPS will be used?
See, number one, explosion-proof building. Number two, if toxic gases should not be entering. And number three, if there could be any fire rating doors, and those aspects are basically taken care during design and construction of the control rooms.
Okay. With regard to mobile operated foam system, how much is sufficient amount is determined by which factor? I mean, how much capacity would be sufficient to suppress a possible fire incident and judged on what basis?
See, how we design, what is the basis of designing your active fire fighting system? First, fire is defined, then the coverage area, spray density, then accordingly a foam requirement and the cooling water requirements are calculated. Same concept can be applied on the fire tenders. If you have to fight the fire by using fire tender or fire engine, then accordingly applicable capacity should be available in one or two fire tenders, so as subject fire could be extinguished and controlled by the available facility.
What is the maximum and minimum pressure required for the main fire pump system attached to the sprinkler system on site?
That depends like how much density you need and how far is the water sprinkler system from the pumping area, piping network. So the minimum pressure what you need, the spray density you need at the destination, that should be supported by the pump. It may vary from, let's say, 5 bar to maybe 20 bar.
Okay, next question. In industries, how much distance required by for the fire hydrant?
See, those are the calculations and coverage area and the pressure available in the fire hydrant and fire ring main or the pumps available.
Okay, next question. Deluge valve installed in pre-action systems. So what is the difference?
See, deluge valve is a valve which is required to start active firefighting system in case of any emergency, and it can be named either way. See, like there's a question about challenging. See, the firefighting, designing of a firefighting system, it is a routine activity. These are being designed for each facility, more or less. We don't consider any project is a challenging. So for each project, there is a new learning. And there's a part of the life when you work on the projects, you come up with the new challenges and you try to solve them. But as such, firefighting, designing of firefighting, active or passive, whether it is a water-based, foam-based, or inert gas-based, is a normal routine and routine work, no issue. Okay, sir. So this is the question answer at this session, and now we'll have a question answer at the end also. So over back to Mr. Frasit.
Thank you, Mr. Ejaz. Up till now, we have discussed how we design the sprinkler system. Now we will discuss how we design the gaseous flooding system. This is the demonstration of the FM200 automatic activation. This is the server room. Detector zone 1, detector zone 2, divided into two zones, zone 1 and 2. This is a network. There's a fire detected in zone 1. Zone 1 detector is activated. Then the signal to the extinguishing control system is received, and the alarm bell is activated. Now the smoke is in the zone 2 as well. So zone 2 detector is activated. Please discharge alarm or horn is activated. Shut down air condition and all the ventilation system is proceeded. So there is a time delay of 60 seconds. Countdown holding can be executed by using the abort station manually. So after these 60 seconds, electrical signal to the solenoid is activated, a valve is released, and the signal to the extinguishing system is provided. Then FM200 is discharged and extinguished the fire. So this is the example of gaseous flooding system. So what were the recommendations and how we have designed the gaseous flooding system? Considering the recommendation of our FRA report and design job scope by the client, following is the scope of work for the automatic gaseous flooding system in the main control room building. Basic engineering for the installation of automatic control flooding gaseous extinguishing system for main control room, including the powerhouse control room and UPS room at main control building, offices and meeting rooms are not included in the scope. What are the design criteria we have selected for the flooding system design? As for the scope of work, the main control, including powerhouse control room and UPS room in MCR building, are considered for the design of total flooding gaseous suppression system. 50 bar gauge Novec 1230 clean agent is considered as per decision by the company. Novec 1230 system design is as per NFPA 2001. Design concentration of Novec 1230 at room temperature of 21 degrees C is taken as 4.725% as per recommendation by vendor according to NFPA 2001. Flooding factor is referred as 0.6873 kg per cubic meter as per recommended by vendor according to NFPA 2001. Dimensions of the MCR building are referred from existing layout drawings. The dimensions are also verified during the site survey. Central banking system and selector directional valve concept is considered. 100% connected standby clean agent filled cylinders were considered for designing the gaseous flooding system. NOVAC 1230 clean agent demand calculations, how we calculated the demand of this NOVAC 1230 clean agent. The total area of the main control room and powerhouse control room was 198.81 cubic meter. These dimensions are taken from the layout, and we also verified these dimensions in the site survey as well. Room of the height was 2.7 meters. Ceiling void height between the ceiling and the roof was 0.41 meter, and floor void height was 0.25 meters. So these height measurements are taken during the site survey. So room volume we have calculated, ceiling void, floor void, and total volume we have calculated by adding the room volume plus ceiling void plus floor void, which is equal to 668 cubic meter. Now the NOVAC 1230 minimum agent requirement was total volume into flooding factor. Flooding factor is 0.6873 kilogram per cubic meter multiplied by total volume. Now with this, we know that how much NOVAC 1230 is required for this room, for the main control room plus the powerhouse control room as well. Now this is for the UPS room. This was the total area of the UPS room, 60.47 cubic meter. This was the room height, ceiling void height, floor void height, room volume, ceiling void volume, floor volume, total volume is came up to 203. So similarly, by multiplying it by the flooding factor, we came to know that how much NOVAC 1230 is required for this UPS room as well. This was the layout we have used for the calculations. So as central banking and selector directional valve concept is considered, so the design of NOVAC 1230 capacity of the system is on the basis of highest in the demand room. The clean agent demand for MCR is the highest, so its clean agent demand will be the governing scenario in our calculation. Quantity of NOVAC 1230 clean agent required is 460, which is the requirement for the MCR, and total capacity of one cylinder is 92 kgs. So how many cylinders we need for the NOVAC 1230? For the main cylindrical bank requirement, 5 cylinders, and for the reserve, 5 cylinders as well. Similarly, now we will discuss the foam system design. So based on the recommendation of FRA report and the scope provided by the client, we have to perform following modifications. We have to install 100% connected reserve system to have extended fire protection, and at the same time to replenish the foam concentrate in the main system, and to check the adequacy of existing foam system piping diameters as well. Then we have to upgrade the existing pressure proportioning system to bladder tank foam proportioning system, as bladder tank system stores the foam in the bladder and does not allow water to mix with foam. In bladder tank, foam is stored within the bladder and there is no contact with water inside the tank. When seawater mixes with the foam concentrate, and impurities in seawater such as shells, marine growth, algae might mix with the foam concentrate. The system can get blocked and will not be available while needed. The existing foam chambers do not match with NFPA 11, so this was the gap. These are to be designed as per NFPA 11. So this was the design criteria for the foam system design. Total foam generator stations were 4. Existing foam storage tanks are PPT, pressure proportioning tanks. Existing 4 pressure proportioning tanks, foam storage tanks to be replaced with the bladder type. because blender type have advantages over this PPT foam storage tanks. Total oil tanks to be protected are 14. Out of 14, 8 were floating roofs, 6 were fixed roofs. And then NFPA 11 is mainly referred for carrying out the calculations for the foam system design. 3% fluoroprotein foam solution is considered as per existing system and FRA report. Full surface fire protection is considered for fixed foam roof tanks as per NFPA 11. Rim seal fire protection is considered for floating roof tanks as per NFPA 11. Application rate for fixed roof tank storage tank is considered 4.1 liter per minute per meter square as per NFPA 11 table 5.2.5.2.2. Application time for fixed roof crude storage tank is considered 55 minutes, and for fixed roof diesel oil tank it is considered as 30 minutes. Reference is NFPA 11 table 5.2 5.2.2. Application rate for floating roof tank is considered as 12.2 as per NFPA 11. Application time for floating roof tanks is considered as 20 minutes as per NFPA 11. And the number of hose streams for each tank, minimum operating time of 10, 20 or 30 minutes and discharge rate of 189 liter per minute based on the simultaneous operation of the required minimum number of hose streams is referred from NFPA 11. Foam demand for initial piping filling of the particular tank is calculated from length and diameter of the piping for that particular tank. Total foam demand for a particular oil tank is calculated by adding foam demand for the tank firefighting, foam demand for hose stream, and foam demand for initial piping filling. Fire water operating pressure at inlet of new blender type foam tank is taken as 10 tanks, and capacity of the foam concentrated blender tank is selected on the basis of highest total foam demand by the tank. Number of foam chambers calculated on the basis of NFPA 11 for floating roof tanks and NFPA 11 table 5.2, 5.2.1 for fixed roof tanks. The foam chambers to be equally spaced along with circumference of the oil tanks. Foam demand and capacity calculations. How we calculated the demand of the foam and the capacity. So there are two foam generator stations installed in the tank's farm area, TFA, for the fire protection of 4 oil storage tanks. The total number of oil storage tanks to be protected by this foam generator station number 1 are 2. One was floating roof and one was fixed roof tank. So these are the details of the oil tanks to be foam generator station number 1. Storage tank A, which was floating roof. The service of this storage tank is bared crude oil. Fuel type is flammable liquid. Type of roof is floating roof. Ream seal fire protection is required for this type of tank. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meter at the floating roof. Reference for dam with GA drawings we referred for tank A. So this was the foam demand calculation for storage tank A. Diameter of a tank was 30.49 meters. Radius was 15.25 meters. And then radius of a tank without the radius of a dam was 14.65 meters. Height of the tank A was, floating roof tank was 14.6 meters. We calculated the area pi into radius of the tank square minus radius of the tank without the radius of a dam. We come up with 56.3 meters square. And then foam solution flow rate for tank A, area multiplied by this 12.2 LPM per meter square, we got 687.02 liter per minute. So this is a foam demand calculation for this was the foam solution rate for tank A. So foam solution is this into 20 minutes, we came up into 137.40 liters. Foam concentrate demand for tank A, liters into 3%, 412.21 liters. Foam concentrate for host streams, two number of host streams. So multiply by 189 LPM, multiply by 30 minutes for the host streams into 3%, we come to know that it is 340.2 liters. So foam concentrate for piping filling is 61.1 liters. So total foam demand will be the foam concentrate demand for tank A plus foam concentrate for host streams plus foam concentrate for piping filling. So total foam demand will be 813.5 liters. Similarly, we calculated the for fixed roof tank B as well. The service of this tank is pump run crude oil. Fuel type is flammable liquid. Fixed roof, full surface fire protection is required for this. Diameter of the tank B was 7.92 meters. Height of the tank was 9.8 meters. Surface area we calculated as 49.24 meters square. So for the foam solution flow rate for tank B will be area into 4.1. We come to know that it is 201.88 LPM. So the foam solution demand for tank B for 55 minutes is 11104 liters into 3%, 333.11 liters. And the foam concentrate for hose piping filling is 10.6 liters. So total foam demand is calculated as foam concentrate for piping filling plus foam concentrate for hose stream plus foam concentrate for concentrate demand. So in this way, we calculated the demand calculation for storage tank B. Similarly, for foam generator station number 2, the number of oil storage tanks to be protected by this station was floating roof tank. It was the service of this storage tank was crude oil storage. Fuel type is flammable liquid. Type of roof is floating roof. Rim seal seal protection is required. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meters at the floating roof. So diameter, radius, and radius without the radius of the dam, and the tank height was 14.6 meters. The dam area, foam dam area, and then the foam solution flow rate multiplying by 12.2, the foam dam area, it comes 1667.55 LPM. So the foam solution demand for tank C into 20 minutes, and the foam concentrate demand for tank C 3%. So it will be 1000.53 liters. And the for foam concentrate for the host stream, it is 510 liters, and for the piping film, it was 216.02 liters. So the total demand foam demand was foam concentrate demand for tank C plus foam concentrate for host streams, and for the piping filling, it is 1776.85 liters. So the bladder tank main and reserve capacities, according to the above calculations, following would be the foam tank capacity. Main foam generator station 1 bladder tank 900 liters. And for station, because why it is 900 liters? Because the total foam demand was 400.5 liters, and for the 100% reserve foam generator is also required, which is also 900 liters. And then foam generator station number 2, main foam generator station 2 bladder tank, the requirement is 1800 liters capacity is required, 100% with 100% reserve. So 1800 is because the total foam demand is 1776. So for station A, there is some calculation issue. So it is normally it should be 400 or 450 liters. So in foam system design, foam chambers calculations. So for the number of foam chambers for tanks are calculated on the basis of NFPA 11. For floating roof tanks and NFPA 11 for fixed roof tanks, the foam chambers to be equally spaced along with circumference of the oil tanks. Below are the calculations of the foam chambers of all the tanks. So for tank A, which was the floating roof, diameter of the tank, circumference of the tank, spacing between each chamber is 24.4 meters. So minimum foam chambers required are circumference of the tank divided by the spacing between each chamber. We will come to up to 4 minimum foam chambers requirement. Similarly, for fixed roof tank, diameter of the tank and minimum foam chamber required is 1. For floating roof tank C, the diameter of the tank was 73.15 meters. Circumference was 229.8. Spacing is as per the NFPA standard 24.4 meters standard. So circumference of the tank divided by spacing between each chamber, the requirement for minimum foam chambers is 10. So this was the summary. Foam generator station's capacity for foam generator station 1, 900 liters or 450 liters. Foam generator station 2, 1800 liters. So existing foam chambers for oil storage tanks as per NFPA 11 for storage tank A was okay. Existing number of foam chambers are more than the minimum requirement as per NFPA. For tank B and C, similar results came up. As per NFPA 11, the existing number of foam chambers are more than the minimum requirement as per NFPA. Now, how we calculated the fire water demand. The purpose of this part of the case study is to present the sample results of the fire water calculations carried out to determine the capacity of fire water pump requirement, fire water storage tank capacity, foam portioner and storage tank capacities. So fire water requirements, the maximum fire water demand estimation is based on the assumption that only one major incident occurs at one given time fire scenario likely to occur within the installation as per NFPA 14. So there will be no any multiple occurrence of the fire. 30% loss from the fire water design rate can be expected to occur due to wind and evaporation. So these 30%, this type of information we will use in the upcoming slides. We will multiply by 0.3, something like this. So we have to stay focused on these wordings. So 30% loss from the fire water design rate can be expected to occur due to wind and evaporation. Fire water storage of 8 hours duration has been considered. The fire scenarios considered for projects are storage area, tap area, TAP, and marine port area or utilities and offsite area. So what were the scenarios? Below scenarios has been assumed for the calculation purpose only. Scenario 1 was fire on mixed naphtha storage tank A. Scenario 2, fire on the light naphtha storage tank D. Scenario 3, fire on the paraxylene export storage tank G. And scenario 4, fire on benzene export storage tank J. Scenario 1, which is the fire on mixed naphtha storage tank A, it was the external floating roof tank. Rim seal fire is considered as a credible scenario. Fire will be extinguished using foam solution by creating foam dam of width 0.6 meters at the floating roof. Cooling adjacent storage tank A, B and C. The exposed surface is a half perimeter of the shell in front of the flame radiation. So the diameter, how we calculated the foam calculations? It starts by the dimensions, diameter of the tank, height of the tank. By the formula, we have calculated the foam dam area, foam solution, applicable rate for external floating roof tank as per NFPA 11 table B.1 is 12.2 liter per minute, which we have also used for the previous calculation as well. Foam solution applicable rate of for tank foam dam area multiplying by the foam solution application rate of external floating roof tank. It is 1905.88 LPM, or in cubic meter per hour, it is 114.35 cubic meter per hour. But considering 3% foam application, so foam concentration required for tank area into 3% foam application, 3.43 cubic meter per hour. Foam application duration for tank 20 minutes. So foam concentration quantity for tank will be equal to foam concentration required for the tank multiplied by the foam application duration. It will be 1.14 cubic meter. Water required for making the foam solution for tank, it will be area, foam concentration, the area into foam concentration quantity of the tank into 0.97. So we have the answer is 36.97 cubic meter, which is the water required for making foam solution for the tank. Similarly, for dike, only oil spillage is considered in the dike area since it is not practical to cover the whole dike with foam. 450 liter per minute hose reels to be used on the spill for 30 minutes, which is largely above the minimum requirement as per codes and standards used. Foam required 1.62 cubic meter and water for 52.4 cubic meter. This shall be facilitated by the portable monitors. So this is for the cooling water calculations. So the exposed surface area of nearby tanks considering 3.7 meter rundown tank BNC, this was the area 3199.1 cubic meter square meter. Water application rate as per NFPA, as per APA 2030 section 7.2.1 is 4.1 liter per minute per cubic per meter square. Water rate required for cooling the tanks is area into water application rate. We come to know on cubic meter per hour. So for water requirements for cooling purpose, for 8 hours, it will be water rate required for cooling tanks into 8 hours. We will come up with the fire water requirement, which is 6142.27 cubic meter. An additional fire water demand of 720 cubic meter per hour is envisaged considering simultaneous operation of 6 portable fire water foam monitors. Requirement for portable monitors shall be 10.8 cubic meter for 30 minutes operation. So this was the summary. Extinguishing storage on fire, water rate considering contingency, then fire water demand, then foam solution rate considering contingency, then foam demand in cubic meters. Similarly, for scenario 2, which was fire or light naphtha export storage tank B, it was internal floating roof tank. Rim seal fire is considered as a credible scenario in this case as well. Fire will extinguish using foam solution by creating foam dam of 0.6 meter at the foam roof. Also, foam will be supplied to the dike area of concerned tank. Cooling adjacent storage tanks E and F is also required. So similar calculations for this as well. Diameter, height, foam dam area will be 149.78 meters. Then foam solution application rate of external floating roof tank as per NFPA 11 table B.1 is 12.2 liter per minute per meter square. So the foam solution application rate will be foam dam area into this application rate. We came to the answer 109.64 cubic meter per hour. By considering 3% foam application, the foam concentration requirement for the tank will be this foam solution application rate of the tank into 3% foam application, and foam application duration is 20 minutes. So the foam concentration quantity for the tank will be this foam concentration required for tank multiplied by the foam application duration, converting into hours. Water required for making a foam solution is 35.45 cubic meter. Similarly, for dike, only oil spillage is considered in the dike area since it was not practical to cover the whole dike with foam. 450 liter per minute hose reels to be used on the spill for 30 minutes, which is largely above the minimum requirement as per codes and standards. Foam required 1.62 cubic meter and water 52.4 cubic meter, which shall be facilitated by portable monitors. For the cooling water calculation for the adjacent tanks, we have calculated by considering 3.7 meter rundown. We have calculated the area, water application rate as per APA 2030 section 7.2.1. We came to know the water rate required for cooling of the tanks, the water application rate multiplied by the total area 2050.76 cubic meter per hour. Into 8 hours, we will have the fire water requirement for cooling purpose as well. So this was the summary cooling water calculation summary for tank D. Similarly, we have calculated for the other two scenarios. Scenario 3, fire for on paraxylene export storage tank G. Similar calculations for this scenario as well. Similar calculations for the cooling water. And similarly for scenario 4, which was fire on benzene export storage tank, we have calculated in a similar manner. Area and then foam solution application rate of external floating roof tank, and then foam solution application rate for the tank, and then considering 3% foam application, we came to know water required for making foam solution for the tank, and similarly for the dikes, and then cooling water calculation for the adjacent tanks. So we have calculated in a similar manner, which we have performed calculations for scenario 1 and scenario 2. So this was the calculation requirements. A fire water demand of 4,000 cubic meter per hour is envisaged for TAP area. A fire water demand of 720 cubic meter per hour is envisaged considering simultaneous operation of 6 fire water monitors. Utilities and offsite area, a fire water demand of 360 cubic meter per hour is envisaged considering simultaneous operation of 6 fire water hydrants. So the largest fire water demand at the UNO facilities is 4,000 cubic meter per hour in TAP area. The foam reserve of foam 8 FFF concentrate at 3% to be provided, considering 30% contingency at storage locations are as follows. Foam concentrate tank capacity for mixed naphtha storage tanks, 1.5 cubic meter of 2 tanks. Similarly, for light naphtha storage tanks, similar, and then for paraxylene storage tanks, 1.2 cubic meter of 2 tanks, and the foam concentrate tank capacity for benzene storage tanks is 1 cubic meter of 2 tanks. For the usage of portable foam monitors, a foam reserve of 16 cubic meter of FFF concentrate at 3% is to be kept in the facility. Now fire water pumps. The 1,022 cubic meter per hour capacity of fire water pump is sufficient to meet the above fire water demand. The design of the pump shall conform to NFPA 20 requirements. Therefore, the configuration of the fire water station will be as follows. 4 fire water pumps will be operated, 3 electric driven and 1 diesel driven. Fire water pump capacity shall be 1,022 cubic meter per hour. 1 fire water diesel pump will be standby. Fire water standby pump capacity shall be similar. 2 jockey pumps with 60 cubic meter per hour of the capacity is required. The fire water storage capacity should be 8 hours of the full flow demand of the fire water pump discharge at 100% operation or depending on the severity of the incident. In order to offer an overall 8 hours firefighting at full flow demand, 2 fire water storage tanks of 1600 cubic meter maximum capacity shall be provided. So we have discussed the active fire protection system. Now we will discuss the case study which was related to the passive fire protection. We will discuss what was the project background, what was the project objective and scope for passive fire protection. Project objective was to conduct a fireproofing integration system. To conduct the passive fireproofing integrity management study for fire zone 14 as the pilot project of the onshore gas processing plant in client's facility against the requirements of the latest edition of APA 2218. This study was required to support the closeout of actions from the audit of the PFP at the plant, passive fire protection at the plant. The scope of this case study was to undertake a gap analysis of PFP requirements for an area which was fire zone 14 as a pilot project of the onshore gas processing plant in client's facility against the requirements of API 2218 and other relevant industry guidance. The scope of work includes to identify any areas where either PFP can be removed or additional PFP is required. Then the scope of work involves the review of the fireproofing of pipe sports for the sample of the area of plant based on the learning from the Velosi incident. Then provision of technical information and estimation of the cost for undertaking a gap analysis review of PFP for the balance areas was also included. The scope included the gap analysis for the fireproofing of pipe sports against new version of APA 2218 for the other areas of the site and identification of any areas where either PFP can be removed or additional PFP is required. Then condition assessment was also a part of the scope involving the assessment of the existing condition of PFP for the other units. These were the project milestones. Development of passive fire protection integrity management framework. Then development of the passive fire protection operational performance standards. Then the assessment of PFP requirements for one area, which was we have selected as fire zone 14 as a pilot project against the requirements of client's design specifications, latest edition of APA 2218 and other relevant industry guidance. And then to identify the gaps and any areas where either PFP can be removed or additional PFP is required. Then the project milestone was the site visit and the fireproofing inspection to assess the condition of PFP and identification of any areas where either PFP can be removed or additional PFP is required. So following steps were taken out for the execution of the project. Gap analysis study has been carried out based on the visual inspection and collection of relevant information from client. Guidelines provided in client specifications and API 2218 are considered as a basis of this study. Then for each item in the plant, such as pipe racks, multi-level equipment structures, air cooler sports, pipe sports, fire potential equipment, ESDVs, cable trays, and long board valves were assessed as a part of this study. And then based on this study, passive fire protection management framework and strategy is prepared, which shall be used for the implementation of gaps in the other areas of the plant as well. So these were the deliverables as a part of this passive fire protection study. It involves passive fire protection integrity management framework or strategy, PFP performance standard, anomaly severity levels, gap analysis report, passive fire protection asset register, PMIR for passive fire protection, and then cost estimation for the balance areas. So this was the passive fire protection requirement as per API 2218. These are the transfer line sports, and then these are the transfer lines with hangers in the FSE. These are these equipment structure in the fire scenario envelope. These are the structures supporting fire protection and non-fire protection equipment in FSE. These are the structures supporting non-fire protection equipment in the fire scenario envelope. These are the pipe racks without pumps in a fire scenario envelope. And this line is showing the fireproofing. These are the pipe racks with large fire potential pumps in a fire scenario envelope.
Full fireproofing is required.
Yes. And these are the air fin fan coolers where the fire proofing is required. So no fireproofing on the stringer beams that do not support vertical loads, and consideration of the fireproofing stringer beams that support vertical loads for the fin fan air coolers. So what were the findings? The findings of this passive fire protection study were that the steel structures supporting the fire potential equipment located within the fire scenario envelope shall be fireproofed up to the highest level at which the equipment is supported. Fireproofing applied to skirt of all the fire potential equipment are found satisfactory and in compliance with the project specification and API 2218. The pipe racks are made of precast concrete elements, which itself is a fireproofing material, and extent of coverage is found satisfactory with no integrity anomaly identified. Another finding of this passive fire protection was that some of the pipe supports which are supporting the loads from the line originating from fire hazardous equipment within a fire scenario envelope from the equipment shall be fireproofed. Then for the pipe supports, this needs to be, this red dotted circle needs to be passive fireproofed. And this is the air cooler supports which requires the passive fire protection. And as a part of findings for the air cooler supports, the air cooler support legs on the top of the pipe rack, which are in the fire scenario envelope, are not to be fireproofed in fire zone area 14 as per client product specification and shall be fireproofed as per client specification. So API 2218 section 5.1.2.2, all the members below the air cooler till grade shall be fireproofed. So this is the conclusion of passive fire protection study. All existing passive fire protection are meeting the requirements for the project specification which was provided. As per API 2218 code, most of the items in fire zone 14 are sufficiently protected with passive fireproofing material except air cooler supports. Totally 11 air cooler supports were there and some pipe supports in close proximity to fire protection equipment are not having enough fireproofing. Another conclusion of the PFP study was that the client specification shall be upgraded as per the latest requirement of API 2218 code. Inspection management plans shall be implemented for civil and structural assets for monitoring the passive fire protection. And then cable trays are of fire retardant type, so no cable trays are fireproofed. As per API 2218, protection may be considered if trays with cable servicing neighboring unit run through the fire scenario envelope. A loss control review may indicate need for fire protection as replacement of critical electrical feeder lines and rewiring cable trays after a fire can be very time consuming. Power and instrument cable can quickly be destroyed in a fire, impeding the ability to have controlled shutdown. So these were the conclusions of the passive fire protection study. Now we can take some questions.
And conclude the discussion.
Yeah. Okay, we can take some questions. There's one question here. What would be the fighting strategy of a heavy fuel oil storage depot, given that this sort of fire is not a very sort of credible one?
See, it has to be managed by classical way, right? We know that there's a low flash point product, but same time you have to have a cooling system, you have to have a foam system. Two standard firefighting systems are basically installed.
Okay, next question. In drilling rigs, they install fire pump near mud systems. Please advise.
See, wherever there's a flammable material available, right? So you have to have fire extinguishing facility either by foam, by powder, or by cooling by water. So these are standard requirements basically what you need to follow.
Next question. When false floor of a control room could be protected separate from the room area, what conditions shall be met?
See, false floor conditions point of view, see, it cannot be answered in a short answer. See, if it is a false roof or false floor or the floor itself, the standard NFPA firefighting or fire and gas detection philosophy has to be developed and has to be followed.
Okay.
There's no shortcut for that.
Next question. What type of fire protection systems are most common for natural gas or sales gas compression stations?
See, generally, there is no mechanism to fight the fire for gas containments. The main thing is the isolation on the entry point of view. First of all, ESD valve should be closed, so the entry is closed. Secondly, the VDV valves or vents, whereas pressurized gas could be relieved. So that is the only major remedy. And thirdly, mostly the pressurized gas cause jet fire, and passive fire protection is generally designed to take care of the fire caused by the gas, hydrocarbon gas.
Next question. For water spray systems, how do we reduce the pressure from the main ring up to the spray system on a storage tank?
See, those are naturally designed, and if you go for reverse calculation, then these reverse calculations are done based on the worst fire and maximum water demand. And if the system is designed with that capacity, then you can get required minimum spray density. And if spray density is higher than that, this is always beneficial. So you don't need to reduce, but generally reverse engineering calculations are performed to make sure you get a desired pressure and spray density at the remote hydrant and remote sprinkler or spray point.
Next question. Will the fuel in tanks be usable after deployment of foam to extinguish the fire?
See, it depends. Like if the foam is like the tank is fixed roof or it's a floating roof. If it's a fixed roof, then foam is normally poured on the surface of the oil, and it's required to be removed somehow if the fire occurred. And see, if there's a fire on the tank, let's be practical. It is not a normal scenario. The complete RCA is required to be done, what caused the fire, how the reoccurrence can be managed. And after the fire, it's not easy to restart the facility a second day. There would be certain corrective action with all respects would be required to be done. Cleaning, maintenance, inspection, so the damaged part are not causing the burst or failure of the facility.
Next question. How we can consider the probability of failure in gaseous flooding systems design, how we choose type of sensor, and how we decide its preventive maintenance plan? See,
all the fire and gas detection system is generally designed in accordance with the NFPA 72, and if we follow the standard mechanism, so there is like a vendor selection, the type of detectors, then the reliability, the seal classification, failure rates, previous trend or history of those kind of detectors. If we manage all those actions from type of the firefighting system, its vendor, and the reliability of the detection system and the voting system and number of detectors installed in each area, So combination of all things from management of the life cycle, from design to procurement, procurement to installation, installation to pre-commissioning, commissioning, and then operational maintenance. All those things make system perfect. Otherwise, there are threats always of the failure.
Next question. Can passive fire protection replace active fire protection methods?
See, it's a combination of both, right? And both are generally required. And see, effects of fire can be minimized by PFP, but AFP is required for extinguishing the fire. So it's not the case if you may not extinguish the fire and you depend only on the passive fire protection. Passive fire protection can minimize the effect of the fire. Let's say if there's a fire for 1 hour, so it will prevent, like, a steel structure should not collapse or fall to create a major jeopardy. However, if the fire is taking place for 1 hour, what would be the scenario or situation of the facilities? Facilities would be gone. There could be fatalities also. So the active and passive fire protection both work side by side. And both are compulsory or mandatory requirements.
Next question. Can we shower water on under fire tank or only adjacent tanks to be cooled?
See, let's say if there is a floating roof tanks, and floating roof tanks, the spray is done of the foam on the mainly on the rim seals. Secondly, if it is a fixed roof, then foam is poured on the surface of the tank. Now, cooling is done from outside. The cooling of all tanks, like number one, the tank under fire, cooling can be done from outside, not inside. So as we are not creating sinking of the roof, or we are not throwing water on the surface of the tank, which can cause blowout, or sorry, a blowout scenario or blavey. Secondly, on the fixed roof, if you throw water, the roof may sink. That can cause major jeopardy. So the throw of the water is always on the sides and the foam is on the surface. So there is a normal standard firefighting philosophy for the tank fires.
Next question. What is the difference between water mist and clean agent system?
See, fire mist is like water mist is the foam and like a very tiny particle of the water, whereas the clean agents are like CO2 or FM200, which does not carry any water content.
Next question. What is the applicable limit for cracks observed on skirt of the vessel which is fireproofed?
See, there's FFS requirement. You know, a crack is only on the, I'm assuming crack on the fireproofing material or cement, or if there's any other parts, any other component used. But if there is a crack on the steel of the skirt, then it carries huge risk. So there are NDT, MPI, DPT, UT, those techniques are required to be carried out, and extent of the crack or its FFS in accordance with API 579 to be performed.
Next question. Is it necessary to install foam system on condensate tanks?
See, for all hydrocarbon service pump tanks, some sort of firefighting system is required to be installed, cooling system is required to be installed. So NFPA 2001, API 2001 or API 2030 in accord, and then in combination with NFPA 30, a proper fire fighting system is required to be installed for the tank terminals. And API 2610 can also be referred for details and subsequent guidelines.
Next question. Which PFP design is better suited for cold conditions? An example, temperature below -25°C.
See, PFP is like as per the concrete material, or it could be a mastic material as well. So there are a variety of material available which can be installed, and temperature point of view, PFP is not limited as such. Since we are mostly operating in the Middle East, and our knowledge is for this area, so I'm not sure in like Canada or areas where negative temperature is there, if any other precaution is required to be taken.
Okay, next question. Can we have a velocity above 10 meters per second in the water spray system of the oil storage tank?
See, normal velocity, recommended velocity is between, let's say, 3 to 7 or 8. More than 10 would be too high velocity. It will cause erosion or noise in the system. It may also have other impact on the water spray densities and pattern. So I would not recommend it, but I'm not so 100% sure if some other derivative is there behind this velocity limitation.
Next question. If fire monitor and fire hydrant system installed on tank, then is it still necessary to provide foam system on condensate tanks?
See, hydrants and monitors both are for water, and water cannot be thrown on the surface of the tank or a floating roof. So foam is the only criteria which can help to extinguish fire within 10 to 15 minutes time. And if tank's fire goes more than 30 minutes or so, it may create other dangerous situations like boil over scenarios and so on. So it's not recommended to avoid foam instead of like along with fire water system. Fire water is only for the cooling. Foam is fire extinguishment for the tanks, and that philosophy to be followed.
Next question. Which type of foam injection arrangement is better for fixed roof tanks? Top-mounted foam pullers or injection from tank lower shell?
See, availability point of view and the testing requirement, like functional testing of the availability of the foam. See, top-mounted foam pourers should be top-mounted, but where is the foam making venturi, or where is the foam substrate? Normally, it should be at the bottom, but if it is on the top of the tank, then refilling of those foam substrate could be difficult. So foam pourer is always the top, and the location of the foam substrate is a subject, whether it's the bottom or the top, that is debatable.
Next question. What does the fire and gas mapping study include or cover? Can you elaborate?
See, fire and gas mapping mean if the number of detectors, then fire zoning, combination of the fire and gas detection system, and then coverage of each detector, whether it will be not in that, there will be not any dead zones. For example, if a fire detector is installed on one side of the equipment and fire could be other side of the equipment and this detector may not detect, then coverage area of the detector as well. Then combination of the fire and gas detection system, for example, if there are oxidizing type of fire detectors, then there are infrared type of fire detectors, then there are H2S type of fire detector or hydrocarbon type of detectors, and then there could be smoke, heat. So there should be a combination of detectors so as the incident can be confirmed by the fire and gas detection system effectively. Any false alarm should not be creating any chaos or undue emergency in the plant.
Next question. Which is more efficient in AFF versus fluorine-free foam?
See, these are mostly driven by the environmental conditions. So nowadays, FM200 or CO2-based systems are there, and I'm not familiar with the more details which questioner is asking.
How can we determine that how many detectors or sensors should be used in a specific area?
So that is the cover I explained earlier, the type of the fire zone. Number two, the kind of expected leaks which may come into the area, whether there's any H2S, hydrocarbon, oil, or there could be some other heat and smoke detection. So there's a combination of the type of detectors and their coverage has to be followed while designing fire and gas detection system.
Okay. Is water mist system can be used in an electrical and communication rooms? If yes, how efficient?
Generally, we have not seen the recent history. It could be specific conditions, but in the normal era, FM200 or CO2-based system is being installed.
Okay. Next question. What is the required pressure at fire blader tank to be maintained attached with the steam boiler?
See, I'm not familiar with this question, and I don't know if we need a firefighting system at that location. Okay, sir, so to conclude our discussion, I hope this presentation material was useful, and engineers in the area who attended this presentation would be benefited. So we will also be adding this presentation on the YouTube. And if you have more questions, please don't hesitate to contact us at our web page or at given email addresses. and we will be glad to answer your questions. Thank you very much for today, and look forward to meeting you during our next webinar. Bye-bye.
Thank you.